By the end of this video, you'll be able to confidently design and 3D print a snap fit bracket that perfectly holds any cylindrical handle. These snap fit brackets are extremely useful because they're an easy and convenient way to store brooms, mops, or any other tool that has a cylindrical handle. And without an experienced guide, designing these snap fit brackets and tuning the various parameters involved can be very overwhelming. But don't worry, I did the work, so you don't have to. Why would you want to design and 3D print one of these snap fit brackets? Well, if you're like me, you might have a pantry that doubles as a cleaning closet. And so you might have something like your broom sitting in that pantry, and whenever you go to remove some food, sometimes it tips over, gets in the way, it's kind of a mess. So what you can do is design one of these snap fit brackets that looks like this. You can mount this to your wall and snap it into place. It'll hold your broom or your mop conveniently out of the way using nice vertical storage. That's just one application out of many that this could be useful for. And the first time that I designed a snap fit bracket, I found that it was quite challenging. I didn't have a guide. There weren't a lot of obvious resources that were available on the internet that were useful for the exact application that I had, and that was snapping a cylinder into a bracket. So through trial and error, I printed a lot of snap fit brackets until I found the perfect formula that will allow you to make a great snap fit bracket for any handle that you might encounter. And designing the perfect snap fit bracket could be done theoretically or empirically through trial and error. The theoretical approach would be taking some beam bending equations and calculating the thickness of the arms and the diameter of the snap fit that would achieve the optimal result. And that could be a lot of fun, but the beam bending equations are a little bit unwieldy sometimes, and it's hard to apply them to every situation and get a good result. So using an empirical approach or a trial and error approach, I was able to test various parameters and tune them until I got a result that I was happy with. And now I want to share those results with you. So let's hop over to the computer and I'll show you how to design the perfect cylindrical snap fit bracket. How do you create the perfect cylindrical snap fit bracket? I'll show you how in Fusion right now. We're going to start by creating a variable that can be changed and represents the diameter of the cylindrical handle that we want to hold. So you'll come over here to the Modify drop-down menu and change parameters. This is where we can create variables that we can then call within our sketches. To create a variable, you're going to click on User Parameters. They're called parameters within Fusion. And you'll hit the plus sign right here and enter the name of the variable. We're going to call it diameter. Then you can select the units of that variable. I'm going to use inches because that's what I'm most comfortable with. And here's where we put the value of that variable. So the broom handle that I designed around had a diameter of 0.835 inches. So that's what I'm going to go with here, but I'll show you at the end how easy it is to change this variable. So there we go. We got our variable called diameter. Now we can open up our first sketch. So I'm going to create a new sketch and I'm going to do it in the top plane. And the first thing I'm going to do is create a circle at the origin. And I'm going to dimension that circle, hit D on my keyboard, and I'm going to give it the variable that we just created. So as I start to type in diameter, it appears right here. I can either hit the enter key or I can click on that drop down that appears and it'll give me that value. And you'll always know that you've called a variable because it'll say fx, which is for function, and then you'll see the value that that function is evaluated as. So we got our circle right there. Then the next thing we're going to do is create a construction line. So line, construction, and we're going to draw it from the origin to the edge of our circle. And this line right here is going to define our opening angle of our snap fit, because of course we need to have room to be able to insert the handle. And I just remembered we're going to want a center line as well, because this is going to be a symmetric design, and a center line is a really good way to mirror components from one side to the other. So I'm just going to leave it floating for now. We'll tie it down at the end, but here's my center line going vertical from the origin. And I want to mirror this line over the center line. So I come over here to mirror, and I selected that object, and it automatically assumes I want to mirror over my center line, which is really convenient. So I'm good to hit OK. And now you'll see that if I drag one of these lines, they both move together. So this is perfect. I can now define my opening angle by clicking on these 2 points. And we're going to do an opening angle of 135 degrees. And now we can take our trim tool and we'll trim away the part that we don't want. So now you can see that this is going to be that diameter of the snap fit bracket. And you can see that this is where we would push that handle in, is here from the bottom. Okay, the next thing that we're going to do is create an arc out here, because if we were to just create an extrusion that looked like this, you'd have a really sharp ending point right here that would make it hard to insert your handle, and you might also hurt yourself because you might hit your hand into the end of that. So if we come over to create and do a tangent arc and click on this point right here, then we can create this nice curve right here. And I just remembered, this is an important part right here. We don't actually want this to match the diameter of our handle, or it will just basically fall right through. It'll be able to hold hardly any weight at all, next to none. So we actually want to make this undersized compared to our handle. And what we're going to do is multiply this diameter by 0.9. So it's only going to be 90% of the diameter of our handle. And the way this works is that these two sides of the snap fit are going to act like arms, and they're going to flex outward. And the force of them wanting to return to their original position is what's going to generate the friction that will hold the handle inside. So got that fixed. Now I want to define the radius of this arc as well as the length of it. So I'm going to add a couple construction lines that'll make this easier. I'm going to draw one construction line from the center of this arc over to each endpoint. You'll see right there, that is a construction line. And I'm going to define the radius now by dimensioning. I can either click on the curve or I can click on these 2 points. It's all the same. And we're going to dimension it as diameter, select it right here, times 0.2. So we'll make this 20% of our diameter. And that's because we want this to scale with the rest of our design. If we want to hold a larger object in here, everything is going to need to scale together, including the fin that sticks out right here. But one thing that'll be constant is we'll always make this 90 degrees, so it'll be a quarter of a circle. Okay, that looks good right there. The next thing to do is grab, well, actually, let's mirror this over to the other side. That looks good. We'll hit OK. Okay, it's coming together. Now what we're going to do is use the offset tool, and we'll select all of these lines right here. And you'll see that as we drag this out, we will get an offset curve. And I realize that I still have construction line selected, so I'm going to cancel that, untoggle construction. Now we'll come back to our offset. And we want this to scale with our design as well. So what we're going to do is type diameter, call our diameter variable, and we're going to make this 10% of our diameter. So diameter times 0.1, hit enter, and you'll see that evaluated out to 84 thousandths of an inch. Okay, and now we want to cap the end of this with a nice rounded curve. So come to arc, tangent arc, click on both of these points, and when you select a tangent arc, it'll make the first point that you click tangent with the line before it, but it won't necessarily make the last point that you click tangent. So you'll see this is looking good, tangent right there. This one is not. So in order to fix that, I just come over to constraints, select tangent, I'll select the curve and the line. Now that's fully defined, you can see because it turned black. And we'll now mirror that end cap over. Click OK. Now we got our first closed profile. So this is actually ready to go right here. This will hold your handle that has that set diameter, but most of the time we want to do a snap fit bracket because we want to connect that bracket to something else, like a wall in most cases. So let's design a little connection point over here that could connect to a wall. So we'll draw a line straight back here, and then we'll need somewhat of a flat face to mount to the wall. We'll stop there. Let's mirror these these 3 lines that we drew over here. So you can imagine our wall would be running in this direction, and this would stick out from the wall. So a couple things that we need to dimension is this distance here. And the important principle here is you want enough distance to be able to curl your fingers around and grab the handle that you want to remove from the wall. So I've found that 3/4 of an inch is a pretty good distance that your fingers can fit around comfortably, but that's the principle that you want to design around there. And then we need to decide how wide we want to make the part that mounts to the wall. And depending on how you mount it to the wall, you can make some different choices here. But if you're going to put screws into this, you need to make sure that there's enough room for a screwdriver on the side of the snap fit holder. Because if you think you can insert a screw right here, you're going to find that when you take that screwdriver, it's going to get blocked by the handle that you're holding. So the way I like to dimension this is I like to go from this point right here, which represents kind of like the outermost point of my snap fit, and then the point, you can see it already selected it over here, that's the outermost part of the bracket portion that's on the wall. And you want to give yourself enough space for the screws that you're going to insert. So 0.5 should be enough. If you wanted to be really generous, you could come out to 1 inch. It starts to get a little big right there. So I'm going to go 0.5. That looks good to me. Okay, we're getting close. Now we want to define the width of the arm that sticks out from the bracket portion to the snap fit portion. And we want this to scale with our design as well, because for a larger diameter, we want this to be a little bit thicker, and that's so that the ratio of the part of the arms, I'm calling these the arms, that sticks out from this connection point remains the same. The easiest way to do this is to create a construction line that goes from the center to the width of this connection point, and then we can set an angle here, and we're going to set it to 30 degrees. And just like that, this will always scale with our diameter, which is kind of cool because we didn't even have to call our diameter variable. But the relationship between this angle and the diameter is such that this width will scale with it. Now, lastly, we need to close this profile. So I'm going to create a line, just draw it across. Oh, I'm still in construction line. Forget to do that a lot. We'll draw this line across. And there we go, got a closed profile, and I believe our sketch, it is almost fully defined. The last thing floating is this center line, so I'm just gonna make it coincident with this edge up here, and then of course, the width here is still floating. So once again, if you're using screws right here, you need to think about how these screws are gonna sit in here, and you wanna make this thick enough that you can seat a screw inside of this bracket and still have sufficient strength that it's not going to fail. So you could go 1/2 inch. Oh, that's a little big. Let's go 1/4 inch. I think that'll be good. So now our sketch should be fully defined. Let's see what we're missing here. There might just be some little point that's not tied down. Before we move on, I want to let you know that if you're interested in learning CAD like an expert and you want to confidently know how to create the models for anything you want to 3D print, I do offer CAD coaching, and this personalized coaching will help you learn the fundamentals and the basics of CAD all the way up through the more intermediate and advanced designs. And I focus it around the types of designs that you are interested in and that you want to learn. If you want to find out more information about my CAD coaching program and apply to find out if you'd be a good fit for the program, comment CAD coaching below and I'll send you more information. Now let's get back to the video. Okay, I found what was undefined about this sketch, and it is this point right here does not have a constraint with this point. So what I'm missing is this coincident constraint, and now my sketch is fully defined. And the reason this happens is because when you use the offset tool, it doesn't offset the exact position of the line. So whereas this line ended right here and had a defined endpoint, the line that I offset was still free floating. So that's something to watch out for. Whenever you offset something, grab the ends of the lines that you've offset and add a constraint so that they're not floating around, and you'll be able to get that fully defined sketch. So finish sketch. Now we're going to create our extrusion. We'll select all of our profiles and we'll extrude these up. And right here, this is just going to be a design choice depending on how long your handle is and what you think is a comfortable amount of space to take up. But 1.5 inches, even 1 inch would be sufficient. And the longer you make this, it will increase the holding force of this bracket, but it's not going to be the strongest lever you can pull to increase the holding force. So it doesn't matter quite so much, but we'll go with 1.5 inches here. Now, what we need to do lastly is put the screw holes in. So the easiest way to do this, I like to create a sketch and throw a couple points down. I'm going to create it on this face. And what I mean is you can just grab a point and you can drop it down, and that'll become the center of your hole. And I want these to be mirrored so that they move together. So I'm going to grab a line, do a center line, and before that, I hit P on the keyboard. Or I can just come over here to project include. I do project. I want to project this line in and this line in, hit OK. So now I can create constraints off of them. So here we go now, center line, going from the origin up to the midpoint of that line. And now I can mirror this point across. I hit OK. Now these screw holes are going to move together. And now I just need to set how far I want it to be from the bottom. And better yet, I just want these to be centered, so I can delete that dimension. And I'm going to do a horizontal constraint with the midpoints of this line. Let me see if I can. We'll do it this way. We'll add a point right here at the midpoint. And if I hold shift on my keyboard, that looks like I don't even have to hold shift, but when this triangle appears, it means that's the perfect midpoint of this line. So now I can create a horizontal constraint between both of these. So it'll always be centered, and the only thing left to do is set the distance from the edge. And I forgot that we'll need to project in this edge right here. Okay, now we can set our distance, and I would set the distance from the outside because preferably you want your screw hole to be as close to the outside as you can get it. We'll go 1/4 inch from the edge. Now we can finish our sketch. That one is fully defined, so that looks good. Now when we come to our hole tool, it first asks us if we want to do a single hole or multiple. We select multiple. Now we can select the sketch points that we want to put our holes at. And you can see that the default distance it shows is, or the default diameter is way too big. But we'll fix that in a second. We want the hole to go through the full length of this bracket. So you can just hit all, and you'll see that that cut will now stop at the back side. And for hole type, this is like the head of the screw that you'd want to insert. So I'm going to do a counter bore, and you'll see how that looks in a second, but it's going to allow you to fully seat the screw into the bracket so everything will lay flush. And then we want to turn this into a clearance hole so that the screw can just slide straight through that hole without catching on any of the threads. And then ideally you would use like a self-tapping screw to go into like a wooden wall or a wooden beam, something of that nature. And over here, you select the screw classification. So if you want to do a metric screw, you would do ANSI metric M profile. And if you want to do a screw that is under the standard system using inches, you do ANSI unified screw threads. And I'm going to do the unified screw threads. And you can select the type of head on your screw. I personally like socket head cap screws, but you'll see that you can select whichever one you want, and the socket head cap screw will match the standardized diameter of that head. And then here you select your screw size, and for the smallest sizes in the inch system, they're just assigned numbers, like number 0 is the smallest screw here, number 10 is the biggest, and then after you get past number 10, it just shows the diameter. They're called out by the diameter of the screw. So I'm going to do a number 8 or a number 10 would be an appropriate size for this, but I'm going to go number 10, and then I'm just going to leave the tolerance as normal. I don't need it to be necessarily extra tight or extra loose. Normal is totally fine. Yep, and it's showing I got an error. Sometimes Fusion's a little bit glitchy. Okay, so I'll just do that again. Counterbore, clearance, ANSI unified screw threads, number 10, and it should be happy with me now. Okay, now if I look at a perfect front-on view, you'll see that I should have room to get a screwdriver in there and insert those screws, and then I just want to measure the thickness of this wall, because if it's too thin, okay, so I'm seeing 60 thousandths of an inch. That's a little thin. So I'm going to come back to the original sketch, and I'm going to change this to 0.35. That'll add a little bit of thickness. Now I've added an extra 100 thousandths of an inch here. If I measure it, okay, that's looking pretty good. I feel comfortable that that's going to hold up. All right, so this is our finished snap fit bracket. Although I will add, this looks a little chunky to me, and so I always like to add fillets. So I would recommend filleting these two outside edges. You can try something like 0.1 inches. That looks pretty good. And then I would definitely recommend filleting these two inside edges, because you actually improve the strength of this design by adding a curve there. It'll dissipate the stress if this ever gets knocked to the left or the right. Okay, and that looks good. So this is the snap fit bracket. You'll be able to insert your handle right here. And if you ever need to reuse this design and you want to do it for a different diameter, you'll see that it's as easy as coming in here, you double click. If I want this for 0.5 inches, I just hit OK. And now this is scaled to 0.5 inches. You can see it's a little bit smaller now. And if I want to do something that has, let's say, a really big handle, maybe 2 inches, I hit OK. Now you can see that it has scaled to that 2-inch size. And I've tested the snap fit bracket for everything between 1/2 inch and 2 inches, and it has performed well over that range, and I'll get into that a little bit later. But there you go. That's how you design this snap fit bracket. It doesn't need to be complicated, and you can follow that simple workflow every time. How do you measure the quality of a snap fit design? Well, snap fits are a little bit like shoes. The perfect pair of shoes would be tight enough that they would stay on through all your daily activities, but they wouldn't be so tight that it would be difficult to get them on and off. The same is true of a snap fit. You want it to be tight enough that it will hold the object without it slipping down out of the snap fit. And you also want it to be easy to insert and easy to remove. So there are 2 factors that you want to focus on. Factor number 1 is the holding force, and that is the amount of force that it takes before the cylinder slips. In other words, this is the amount of weight that you can hold in your snap fit. The other factor is a combination of insertion force and removal force, which I just call mating force. That's because the insertion force and removal force are approximately the same. So you want to maximize holding force while minimizing mating force. And that will get you the ideal snap fit design. And what that means is that when you go to push the handle into your snap fit, it'll easily snap in there. It's not going to take a lot of force. You're not going to punch a hole through the wall trying to get it in. And when you're ready to take it out, it's just as easily going to snap right out of there. And when you're away and you're leaving your object hanging there, it's not going to fall. So the way that I determined this formula for designing a snap fit is I tested several different diameters. And I ranged from a 1/2 inch diameter, which is about 12 millimeters, up to a 2-inch diameter, which is about 50 millimeters. And the very first one that I designed was the one for my broom handle, which happened to be 0.835 inches. And so I got the parameters tuned really well for 0.835 inches. And then I extrapolated those out to a 1/2 inch and 2 inches and made some minor adjustments from there. And the way I did this is that I 3D printed some little cylinders that were the diameters that I was testing. And I inserted those cylinders into the snap fit, and then I pushed along one side and measured the peak force that it took for the cylinder to slip. So that's how I got the holding force. And then for the insertion and removal force, I did something similar. I used the digital force gauge, and I measured how much force it took to push the cylinder in and then to pull it out. And these are the results that I got. So for holding force, I measured at a 1/2 inch. The holding force was around 6 pounds. And what that means is that for an object that has the same texture and material as PLA, I could hold an object that's about 6 pounds before it would fall. That's about 30 newtons or 3 kilograms. And that was with the 1/2 inch diameter design. With the one that I created for the broom, interestingly enough, it actually had a lower holding force, around 4 pounds or approximately 2 kilograms. Then with the 1 inch diameter, the holding force was about 9 pounds. And for the 2 inch diameter, it was about 11 pounds. And the reason that I mentioned the material and the texture of the object is because different materials are going to have a different coefficient of friction. So I only tested this for my PLA cylinders that I printed, and these are the results that I got. But if I were to use something with a more slippery handle, which most handles will be more slippery than the PLA unless they're made out of rubber, then if those handles are more slippery, the holding force is going to be a little bit lower. But I would say that most brooms, household objects, are going to be around 2 pounds, 1 kilogram. So if you can get above that 2 pound threshold, you shouldn't have a problem with holding force. And the cool thing is you only barely need to exceed the weight of the object you're trying to hold. So if you want to hold a 2 pound object and your holding force is 2.5, 3 pounds, you're good to go. You don't really get much benefit from going up to, let's say, 10 pounds, unless you want to mount a different object that weighs 8 or 9 pounds onto that same snap fit. Then if we come look at insertion force, you'll see that for the 1/2 inch to 1 inch, the insertion force was pretty close to 5 pounds or about 2 kilograms. But then over at 2 inches, it got significantly harder to insert the cylinder. And I would say that the ideal would be to be under 5 pounds of force. I found that to be satisfactory. And in fact, 3 pounds was probably the ideal amount of force. And in general, you just kind of want to minimize this. But I would say 10 pounds is doable, but it does start to feel like you're really needing to push that handle into the bracket. And then the removal force was very similar to the insertion force. And this is what I suspected, but I just wanted to confirm it myself. But I would say that these had negligible differences, maybe a little bit more variation in the removal force, but all in all, I would just lump that together as the mating force. So I just wanted to show these results to you to show you the process that I went through in tuning these parameters and the outputs that I was looking at. And let's say you want to design a bracket that has a 2-inch diameter, but you don't want the removal force to be up around 10 pounds. What can you change about the design that will allow you to decrease the removal force? Well, if we come back to the design that we made earlier and I edit this sketch, the parameters that you can tune are the diameter of your snap fit and the wall thickness. Those are going to be your two most important parameters, but then also opening angle is going to have an impact. So as you decrease this diameter, what it's going to do is increase the holding force, but it's also going to increase the mating force. So you've got a trade-off there. And then with the wall thickness, as you increase it, it's going to once again increase your mating force as well as increase the holding force. And then with this opening angle, if you make the opening angle larger, let's say 150 degrees, then your insertion force is going to decrease. So that would be preferable. And so in the case where you're doing a 2-inch diameter handle, I would actually recommend having a little bit of a larger opening force. Of course, if you go too big, let's say 1/2 inch, it won't be able to hold anything at all. Your handle will just drop right through. So you need to be less than 180 degrees. And I would say you don't ever need to go tighter than 135, but you could mess around between 135 and maybe 165. That might be getting a little questionable right there though. But there's your opening angle that you can adjust. And then the way I would adjust these parameters in your model is rather than doing, let's say 90% of the diameter, you could try something like 95, and then everything will scale with it. Or if you needed to go tighter, you could try 85%. And then over here with the wall thickness, if you wanted to, let's say, make it easier to insert the handle and pull it out, rather than using 10% of the diameter, you can maybe try 8% of the diameter. You'll see everything scale along with it. Maybe 5%. In my experience, I found that 5% didn't really work. It felt very easy to move the object in and out, but it didn't have very good holding force. So I would say 5% is probably, you don't want to go lower than that. And then 10%, I don't think you really need to go higher than that. And as you know, if you've looked at these beam bending equations, these parameters are not linear with the outputs I'm measuring. However, over a small range of diameters, which I'm defining as 1/2 inch to 2 inches, a linear approximation is somewhat close. And in engineering, a lot of times when you are dealing with a shortened range, you can make linear approximations that are good enough to get you a functional result. So that's why I landed on this 0.9 and this 0.1 and the 135 degrees. But once again, if you're going to the limits of that range I've defined, or you're going outside of that range, that's where you're going to want to tune these parameters a little bit. And that's something you can play around with, especially because you might be dealing with handles of different materials and textures. But that's it. Those should be the only parameters that you really need to tune. Everything else in this model can stay relatively untouched. I hope you've enjoyed today's video. If you have, you should check out some of the other videos on my channel, such as this video where I teach you how to design the perfect cup holder that allows you to fit your large water bottle into the tiny cup holders in your car. And also, if there's a particular video that you'd be interested in seeing, or a particular design that you want me to walk you through, leave a comment below letting me know what you'd like to see. Thanks again for watching, and I'll talk to you again soon.